All right, if we can turn to page 13 in your packet. Okay, so we started this unit talking about area. From area, we talked about different orientations, top minus bottom, right minus left. Then we moved into this method, right? Taking that area, rotating around an axis to create that circular shape. Okay. And now we're going to extend that further, but let's explore and recap this method first. Okay, so we started with the shaded region. Right, y equals square root of x. And then we said that for this problem that we discovered 2 days ago, our axis of revolution was x-axis. We're rotating that 2-dimensional figure around the axis of revolution. And we know that the shape that's created are these circular disks. And we know that we have to draw a radius, right? Radius extends from the axis to the boundary of our shaded region. Okay. And we knew that we're accumulating all these circular disks from one end to the other. So we have to involve circle related information, and that's where the pi r squared comes into play. Pi, big radius, I forgot to put the squared here. Okay, so we are accumulating all these circular disks from one end of the diagram to the other end. Okay, so we're good with that, right? We explored this method, top minus bottom. We explored it, right minus left. So now I want us to look at, what about this diagram here? Okay. So we have a kind of like a leaf-shaped figure that's kind of pointing at a 45-degree angle here. Okay, we're still going to do rotation. We're going to rotate around the x-axis. But what do you notice is difference between this and the previous diagram? Or the shape that's going to come out of this rotation. Yeah, there's some sort of, it's not a full solid like before, right? There's sort of a gap or hole. And when we think about it from that perspective, we know that the volume is not going to be as much because we have to subtract out the gap that is inside this diagram, this kind of bowl-shaped object, right? So the idea is that, well, if I can think of this as circular disks, if I were to slice this object down, maybe it's more like circular rings, right? I'm adding areas of circular rings to essentially create this object. Okay, so let's kind of review a little bit about from a 2-dimensional perspective. So circular ring. What information would you need to find the area of that shaded circular ring portion? Yeah, radius of the big circle and the radius of the small circle. So essentially what we're doing is we're adding infinitely thin rings from one end to the other to adapt for the fact that there's going to be different size holes and circular holes across this entire diagram. Okay, so if we want to subtract the area of the 2 circles to get that ring shape area, then it's pi big R squared minus pi little r squared. We can factor that pi out, just kind of working towards the formula that we're going to be using here. But this only gives us the area of one representative ring, right? What if we want to accumulate that from one end to the other? So this will be definite integral from a to b, pi big R squared minus little r squared. And that's where it leads to the top minus bottom for washer method. Okay, we call this washer method. It's just another word for circular rings here. Typically, we like to pull the pi out in front, just like how you saw with this method. And we're going to be finding not only big radius, we're also going to find little radius. Okay, so that's going to kind of extend our formula a little bit more compared to this method, right? We see a lot of similarities. It's just that now we have to account for the fact that there is a gap or hole that we need to subtract out of our diagram. Okay. Now, another big difference I want to point out to you is look at the axis of revolution in relation to your shaded region. You see how the axis of revolution is up against a flat surface? Because it's up against a flat surface, after rotation, there's not going to be any hole or any gap. But if there's any sort of a gap between the axis and the shaded region, we know that there's going to be a hole. So we need to be able to look at a diagram, look at the axis of revolution, and see how they interact to decide whether it's going to be this method or washer method. Okay. So basically, if there is any sort of a curved region going on, touching is not going to make it a this method. Okay. So basically, it's going to be it's basically pretty restrictive to get a this method going, right? Because we need a flat surface and the axis has to be up against that flat surface. Okay. If it's any other situation, whether there's a complete gap between the axis and the shaded region, or if the axis is up against this curved surface, we're always going to have a hole to subtract out. There's always going to be a washer method. Okay, so we're going to explore the top minus bottom first because these are the ones that are a little bit easier. And then we'll explore the right minus left, which requires a little bit more rearranging and adjustment of our equations. Okay, so let's look at example 1 here. Okay, example 1 says, find the volume of the solid enclosed by the graph of y equals x squared and y equals square root of x. So basically, we're doing this now in full. Okay, revolved around the x-axis. Okay, so here's my dotted line, my axis of revolution. Okay, so just like what we said before, the axis is touching the shaded region, but it's not in full, right? We see all this hole, all this gap. We know that the finishing object is going to be circular rings and not circular discs. Accumulation of those shapes and not of rings and not discs. So we know that we have to find two radius, right? The big radius and this subtract out the hole. Okay, so big radius is the distance from the axis of revolution to the outer or to the further curve. Okay, and little radius is the distance from the axis of revolution to the inner or to the closer curve. Okay, so let's do this. Find any place on your axis, and we're going to start on the axis. I'm always going to have you guys start at the center, right? This is the true center of the object, right? After rotation occurs, the center of this bowl is going to be right at the x-axis. Okay, so put your pen or pencil on the axis, and we're going to extend to the further curve. Extend to furthest. Okay, you can take your radius, and we're going to name that big radius, big R. I should put it down here. Okay. Little radius is the distance from the axis of revolution to the inner or to the closer curve. So start your pen or pencil on the axis and extend to the closer curve. Okay. Now, if you place the big R and little r next to each other, they're always going to, it's going to be obvious which one is big R and little r, right? Big R is going to be the longer, okay, and little r is going to be the shorter of the two. Okay, questions so far? Okay, so let's build our 2 radius before we involve the volume equation. So big radius, we know this is going to be top minus bottom because our radius is vertical. Okay, so this, the curve that's concave down here, this is y equals square root of x. And the curve below here, this is y equals x squared. Okay, so top minus bottom. Okay, let's start with the big radius first. What is the top of the big radius touching? Root x. Okay, start here. Top minus bottom. What's the bottom of big radius touching? 0. So root x minus 0. Okay. Little radius. Start at the top of the little radius. What's the top of the little radius touching? The x squared. Minus, and the bottom is 0. Okay. Okay, we should be ready for our volume formula. Typically, we would have to set the equations equal to each other and find those intersecting points, but the graph is showing that to us. And if we want to do top minus bottom, our bounds are in terms of x. So let's build our bounds here. Our bounds is from where to where? Right, we're stacking these circular rings from one end to the other end, right? From the left endpoint to the right endpoint. Okay. Okay, we're looking at the x values, right? We're looking at the x values here from 0 to 1. Okay, let's see what the formula says. Big radius squared. So we're going to square our big R. Minus little radius squared. Okay, we can work this out by hand, but we're going to practice entering into our calculator. I think this is where using y1 and y2 is going to be really helpful, because especially if you're having to do Washer method multiple times, you can just get that template on your home screen, and the only thing you have to change is R1 and R2, or Y1 and Y2, that represents big radius and little radius. So, okay, so if you have a 36 Pro, you're kind of stuck having to type everything out, but at least with 84, you can save a few keystrokes here. Okay, so under Y1, I'm going to name this, call this square root of x. Under Y2, I'll have that represent the little radius, so x squared. Okay, go back to your home screen. Math 9, our bounds is from 0 to 1. Okay, so on the board there, right, vars, y vars, function y1. I have y1 holding my big radius. And this is nice. You don't have to use parentheses. You can just square. All right, the nice thing about separating this out is that you don't have to use as many parentheses as well. So it's just a little bit cleaner. Minus little radius squared. So I have that stored under y2. And then dx. Try to convert to a fraction if you can. So math, scroll over to num. Sorry, just math fraction. Math 1. Right, what else do we need to include? All right, this is still circle based, so we still have that area of a circle involved, pi is involved here. Units cubed, right? This is, the units is not provided, so for now, we'll just say units cubed to help remind us that we're dealing with a three-dimensional calculation here. Okay, any questions so far? Okay, I do want to highlight two big pitfalls at this point that I see students experience in the past. And that is the issue of drawing the radius incorrectly, okay? What do you think is a common way that students try to create one of the radius with this diagram? Right. Right. That's what we do with area, right? But this is great if we want to find the area of the shaded region. But we're trying to build radius, right? We can't call something the radius if it doesn't include the center, right? It's like going over here and saying that this object, this circular object here, calling this the radius, right? That isn't correct. And same thing here, going to a two-dimensional object and calling that distance the radius, right? So because we're calling the radius, we have to include the axis of revolution, the center of this object. So that's why I always say that when you draw your radius, start on the dotted line, so that as a reminder that you're always including the dotted line whenever you're creating your radius, right? So we can't do this, okay? All right, so this mistake doesn't show up on this method because this method, there's only one diagram and the axis of revolution. So students typically don't make that mistake, but this, it's easy to make a mistake with the washer method because the tendency is you just want to connect the two regions. But remember, this is the true center, right? We're calling this a radius. We're not calling this the height of a rectangle. Okay. Okay. The other issue that I see is writing the radius, writing the volume formula incorrectly. Okay. And what I mean by that is we have to make sure that we square the radius separately. Okay, so we can't do this. We can't say volume is equal to integral root x minus x squared. We can't subtract the radius first and then square everything else. Okay, that's not the same thing. Okay, so I'm going to keep reminding us that in order to follow this formula, we have to square each individual radius separately. Okay. All right, try example. Let's look at example 2. We're going to do another top minus bottom orientation, and then we'll switch over to right minus left, where there's more steps involved having to rewrite our equation. Okay, so here's example 2. Find the volume of the solid created by revolving the function y equals x squared plus 1, bounded by the line y equals 2, revolved about the x-axis. Okay, so this is our axis of revolution. Okay, let's build our graph here. Okay, y equals x squared plus 1. That's just a parabola that's shifted up 1 unit. Y-intercept at 1. Okay, bounded by the line y equals 2. So there's our enclosed region, right? Revolved about the line y equals 0 or x-axis. Okay, so we can tell that it's not even touching, right? This is complete gap. This is definitely going to be washer method. But I want to keep reminding us that even if the dotted line was up against the curved region, that is still a washer method, right? Touching at one point is not good enough. There's actually only going to be one place that this can be this method. Where's the only place that we can have this shape be this method involved? If the axis is where? Okay, where's the flat surface? Y equals 2, right? This is the only place for this diagram that we can even have any this method involved, right? So if it's over here, it'll be washer method. If it's over here, it's washer method, right? So any touching is not good enough. We got to have up against a flat surface. So typically, it's a lot easier to create a washer method scenario than it is for this method scenario, right? You got to have a flat surface. You got to have that axis up against that flat surface. Okay, so this tells us washer method. We have to involve 2 radius. So again, let's start on the axis of revolution. Okay, extend to the further boundary. We're going to go up until we hit as far as we can go, the furthest boundary that we can hit. Okay, we'll call that big R of x. Pick a point relatively close. Start on the axis and extend to the closer of the 2 boundaries, and we'll call that little radius. Okay, it's obvious which one is big R and little r. Big R is going to be longer of the 2. All right, let's build our radius. Top minus bottom. What's the top of big radius touching? 2 minus, what's the bottom of big radius touching? 0. 2 minus 0. Okay, little radius. Top of little radius is on which graph? Yep, the x squared plus 1. Top minus bottom. Bottom of little radius is 0. Okay, cleans up, right? Just becomes 2 and x squared plus 1. We can drop the zeros. Okay, what else do we need to find? The bounds. Okay, how can we find the bounds? Yeah, let's find the intersection, right? Set the functions equal to each other. Set the line equal to the curve. Okay, subtract 1 from both sides. X squared equals 1. Take the square root. What happens when we take the square root? Plus or minus, right? We have 2 values that come out of this. So -1 and 1, and those are the bounds that we have. Right, we're stacking these circular disks from -1 all the way to the other end, to +1. Okay, I think we're ready for our washer method, top minus bottom formula. So we start inserting information in, right? We have our bounds, we have our big radius, we have our little radius. And again, we'll make sure that we square them separately, okay? Square them separately. Okay, big radius squared minus little radius squared. Okay, so this is where, you know, if you have the template built already in your 84, you can just keep calling this and just change y1, y2, and maybe change the bounds. We can really save the amount of keystrokes that we have to do, especially if we're having to do these washer methods over and over again. Okay, so I'll let 2 be big radius. I'll let x squared plus 1 be little radius. Go back to my home screen. Scroll up to my previous entry, and all I'm going to do is I'm just going to change my bounds. Right? I already have my big R squared, little r squared already set up. from -1 to 1. Okay, see if we can convert that to a fraction. If you can, great. If not, you'll just round to 3 decimal places, or you'll just approximate the 3 decimal places. So here, 64/15. And don't forget pi. Okay, any questions so far? Yeah, right now, I really just want to allow us to focus on trying to draw the radius correctly, right? That we're always starting on the axis and moving out towards our boundary. We never want to connect the boundary of the shaded region, right? That's never going to be anything involved, especially not with washer method, right? So we have to kind of resist that temptation to do that because it's not part of what we're looking to find.
What would happen if you only got one solution for x?
If you only got one solution for x, that would mean that the other boundary we have to set another. We'll have to set up another intersection. But typically, because we only have 2 equations here, we know we're looking for 2 solutions, and we should always get 2 solutions that way. Now, you could also do this if you had your graphing calculator. You'll be able to do intersections. But if you're using your scientific calculator and you're only getting one solution, but you know that there's a second one, you can start on further away so that it can look for the other solution. Yeah, so you can have it look for 2 solutions if you give it 2 starting points. Otherwise, if you only give it 1 starting point, it'll only get you 1 solution. Yeah. Okay, questions? Okay, let's go to the back page. I want to skip example 3. Example 3 is basically like example 2. It's just the axis is further up. We still do top minus bottom. We still do washer method. I want to explore a right minus left. What if we had a vertical axis of revolution? So we're going to look at example 4, but I'm going to turn your attention to the formula that we have here, right? A vertical axis of revolution means that we have to draw a horizontal radius. If you draw a horizontal radius, you got to do right minus left. If it's right minus left, then you have to rewrite your equation, right? So washer method with horizontal radius is going to be the most extensive problem, right? We got to involve 2 radius. We got to involve rewriting the equations. We got to involve rewriting the bounds or adjusting our bounds to be in terms of y. So these are the ones that are the most time intensive. Okay. All right, so let's see if we can go through that slowly and at least get more comfortable with that, with the steps involved. Okay, so same diagram. Find the volume of the solid created by y equals x squared and y equals square root of x, revolving about the line x equals -2. Okay, this is not a horizontal line. This is a vertical line here. Okay, so let's extend the graph a little bit to the left. Doesn't have to be to scale. Just going to indicate that this is -2. Vertical axis means our radius has to be perpendicular. If it's perpendicular, it has to be horizontal. So, and we know there's a gap, right? There's a gap. We know there's definitely washer method. Okay, so start on the axis, okay, and extend to the furthest boundary that you can take your line. Furthest boundary of your shaded region, okay? Call that big R. All right, put your pen and pencil on the axis of revolution, extend to the closer of the two boundaries, and call that little r. All right, as soon as you see a horizontal radius, you know that there's more work ahead, right? Because these equations are not set up for right minus left. These are set up for, these are set up for top minus bottom, right? So we have to rewrite these equations here. So this curve here, kind of like that. That's the y equals x squared. How can I rewrite it to get it ready for what I need? X equals what? Root y. Now, technically it's plus or minus root y, but the negative root y is over here, which is not part of our diagram, so we're only going to do the positive root y. Okay, what about the y equals square root of x? How would I rewrite that? Yeah, square both sides. I want to get x by itself. So if I square both sides, I get x equals y squared. All right, let's build our two radius here. Start with big radius, that's a longer one. Let's look at the right endpoint. Right minus left, what is the right endpoint of big radius touching? Which graph? Root y, okay, start with that. Minus, what is the left endpoint of big radius touching? Okay, careful here, right? Right minus left, if there's a negative from the radius, we got to keep track of both negatives, right? Right minus left. The first minus is for the formula. This second minus is with the line itself. Okay, is everybody okay with that? Right, little radius. Right minus left. What is the right endpoint of little radius touching? What's the adapted equation? Y squared, okay. Minus, what is the left endpoint? -2. All right, let's do our cleanup. All right, what are the bounds going to be? All right. Oh, sorry, 2. Sorry about that. Okay, y squared plus 2. Okay, so where are the bounds going to be here? 0 to 1. Okay, so we're talking about the y value, right? So we're stacking these circular disks from 0 all the way up to 1. All right, we're looking at the y values, not the x. I know it looks like same thing, right? But we're specifically targeting the y values because that's what the formula says, right? Formula says y1 to y2. If we're doing right minus left, we have to use bounds in terms of y. Okay, so. Make sure you're squaring your radius separately. You see y's on paper, but in your calculator, you're using x's. Go to your calculator under y1. I'll type in square root of x plus 2. or y2. We'll do x squared plus 2. Go back to your home screen. I can just pull up my previous entry and just adjust the bounds. Try to convert to a fraction, math 1. If it can't, then you can just approximate to 3 decimal places. Don't forget the pi as well. Side note that I want to have you guys write down. Okay, bounds are your bounds. Lower and upper bounds or left to right bounds are restricted only to your shaded region. Okay, the reason why I bring that up is sometimes I see students, they're looking at their axis of revolution, they see that it's really far away and they feel like they have to include that as part of their boundary. Okay, we don't care about where that axis of revolution is. Okay, your boundary is only for your shaded region. So only look at your shaded region when you're creating your bounds. The axis is only going to be used for your radius and nothing else. We're not going to use it to help us find the bounds involved. Okay, any questions here? Okay, so these are the most time-intensive ones, where not only is it washer method with 2 radius, but you have to do horizontal radius, meaning that you have to adjust your equations, rewrite the equations, and you have to make sure that your bounds are in the correct variable, right? So a lot of things going on, but hopefully, we've kind of done enough over the past couple of days to kind of build up to this so that we're kind of almost expecting these steps, because we've done right minus left for area, but we've also done right minus left for this method. Okay, so we're going to try to get some more practice problems in. So go to page 15. Okay, read number 1. Draw your axis of revolution. See if you can look at the diagram and convince yourself whether this is going to be this method or washer method. Okay, page 15. Okay, so it says let the region R be the area enclosed by the function y equals square root of x minus 1. That's the radical here. The horizontal line y equals 1 and the y-axis. Okay. Find the volume of the solid generated when the region is A, revolved about the line y equals -3. Kind of drawn for us already, right? Okay, obviously, we see that huge gap. We know this is going to be washer method. but it's really easy to do washer method, right? Because if it's up against a gap or up against, if it's not up against a flat surface, it's going to have to be washer method. Actually, for this diagram, there's only 2 places that this could be disk method. Can you guys identify where those places are? Where are the only places where this could actually even be a disk method problem? Y equals 1, okay, up against a flat surface. Where else? Yeah, x equals 0. Right. So just keep that in mind, right? If you're having trouble deciding whether it's disk or washer, most of the time it's going to be, right, it's very restricted for this method, right? You got to find a flat surface and the axis has to be up against it, right? If it's any other situation, touching is not good enough, right? It's got to be up against a flat surface. Okay, washer method. All right, so start on your axis of revolution. I know the temptation for a lot of students is they just want to connect those 2 graphs, right? But we do that for area, but we don't do that for washer method. So start on your axis and extend to the furthest boundary you can find. Start on the dotted line and extend to the closer of the 2 boundaries. You look at them next to each other. You can tell the one on the left is longer, that's your big R. The one that's shorter is going to be little r. Okay, let's build our big radius. Top minus bottom. Right. What's the top of big radius touching? Okay, 1, right? Minus. Good. Remember, sometimes you got to keep track of multiple negatives, so don't skip out on that, right? We can't just say 1 minus 3. That's not the same thing, right? So 1 minus a negative 3. Okay, top minus bottom. What's the top of little radius touching? Minus. Yep, the bottom of little radius is also touching negative 3. Okay, let's clean this up. Keep track of our negatives there. 1 plus 3. And then 1 minus negative 3, that's going to, well, negative 1 minus negative, that's negative 1 plus 3, which is 2. Okay, what else do we need? Balance. Okay, so we're stacking these circular rings from 0 all the way to this point. I know that right now they're kind of giving that to you, but not every diagram is going to be as generous as this. So we want to just make sure that we can find this either algebraically or numerically or graphically. So what can I do to find that intersecting point? Yeah, set equal to each other, but you can also graph these 2 points and use the intersection feature, or on your 36 Pro, you can also do root x minus 1 equal to 1 and do num solve with that. But I think it's easy enough to solve by hand. Okay, add 1 to both sides, square to get that x by itself. Okay, we should be ready for our volume formula here. Pi, that's the integral from 0 to 4, big radius squared, minus little radius squared. Again, we have to separate the exponents. We can't just subtract and then square once, okay? Right, in your calculator, I'll let 4 be big radius, y1. Little radius, I'll have it stored under y2. 0 to 4. Let's see if it'll convert to a fraction. It doesn't, so we'll leave it at that. 8.667. Don't forget pi, and then units cubed. Okay, a few minutes remaining. Let's just see if we can start part B. What's different about part B that's going to make this more time intensive? Yeah, we have a vertical axis of revolution, same diagram, still Washer method, but now the radius is horizontal. If the radius is horizontal, we know the equations that's given to us is going to have to be rewritten, right? It's not in the right form. This is built for top minus bottom, not for right minus left. Okay, again, start on your dotted line. Extend to the furthest boundary. That'll be your big radius. Okay, put your pen or pencil on the axis. Extend to the closer of the two boundaries. And that's your little radius. All right, the curve has to be rewritten, right? Y equals square root of x minus 1 is not in the proper form. Add 1, square both sides. All right, we want to get that x by itself. Okay, big radius, right minus left. What's the right end point of big radius touching? Yeah, y plus 1 squared. Minus, what's the left end point of big radius touching? The negative 1. Okay, little radius. What's the right end point touching? 0. That's x equals 0, right? That also has an equation. The y-axis has equation of x equals 0. 0 minus, right? What's the left end point touching? Negative 1. Good. All right, we'll pick this up on Monday. Monday, we're just going to do this worksheet here to practice, get really comfortable with Washer method. You guys have homework for Washer method over the weekend. I'll send out a reminder on Sunday.